Ants. You know them, you might even hate them.
What? That's right, you heard me. I'm an ant hater.
You may even wonder what purpose do ants serve if not to give you a major headache every time you were a little too late on putting away your sugar jar. Perhaps one evening you may have observed a harmless stray ant and then noticed one more.
You're not so crazy. Hey, you're cute.
And then another, and then several more, and then more and more, and they seem to come from out of nowhere. Wouldn't you know, ant behavior has been studied for years, but why? Ants are easy to observe and represent a collective system. As a collective system, ants can be studied to help understand individual and group relationships. Ants are easy to manipulate in a controllable system. The ants are decentralized, meaning that they don't follow commands from any leader or alpha ant, but instead ants individually follow simple rules. As a group, ant interactions lead to the emergence of complex behavior and cooperative interactions. You may be wondering, if all of this is true, how can I model this computationally? Well, I'm glad you asked. As a decentralized system of agents that follow simple rules, ants make the perfect model for cellular automata. A cellular automaton is a model of a world with very simple physics. They're made up of cells that live on grids. Each cell typically has two states, either on or off, black or white or true or false, etc. Cellular automata follow rules that determine how the system evolves. To examine how cellular automata can be implemented in code, we'll explore an example in Python of a popular two-dimensional cellular automata called the game of life. The game of life has simple initial conditions that yield surprisingly complex behavior, and like LinkedIn's ant, is Turing complete. The life class creates objects with the following attributes. N represents the number of rows and columns in a grid. Mode controls the behavior of border conditions. Array represents the grid, which is an array that contains the data of the cellular automata, and weights, which is particular to the game of life and is used to compute the weighted sum of the neighbors. In step, Boolean is an array where true represents live cells. These are converted to integers. The Live Viewer class is used to generate an animated view of the grid. Running the program prompts the user to enter a rule pattern, and as a result, interesting patterns will emerge. Similar behavior is observed in LinkedIn's ant. In 1986, Chris Langton developed LinkedIn's ant, a four-state 2D cellular automata that captured the emergent behavior observed in ant colonies. Individuals alter their environment, which influences the behavior of other individuals who would then alter their environment and so forth. In LinkedIn's ant, the rules for the cellular automata are as follows. Rule 1. If the ant is on a black square, it turns right 90 degrees and moves forward 1 unit. 2. If the ant is on a white square, it turns left 90 degrees and moves forward 1 unit. And 3. When the ant leaves a square, it inverts the color.
I'm saucing on you. I'm swagging. I'm ballin', have a son on you.
When an ant starts on an empty grid, it eventually builds a series of 104 steps that repeat indefinitely, also known as a highway. This image shows an ant starting from a completely white grid after 386 steps. And then shown here after 10,647 steps, you can see in this image that a highway is being constructed towards the lower right-hand corner. It is believed that an ant will eventually build a highway no matter its initial pattern, but this remains formally unproven. Ant behavior has been studied and modeled in machine learning, networking, and parallel computing. An algorithm known as the Ant Colony Optimization Algorithm, or ACO, has been developed based on ant foraging behavior to find solutions for optimizing paths and graphs, such as a traveling salesman problem. which is the problem of finding a shortest closed tour that visits all cities in a given set. In the natural world, ants wander randomly, and upon finding food return to their colony while laying down pheromone trails. If other ants find the pheromone trail, they'll follow that trail, returning and reinforcing it if they eventually find food. Over time, however, the pheromone trail starts to evaporate, thus reducing its strength. The more time it takes for an ant to travel down the path and back again, the more time the pheromones have to evaporate. A short path, by comparison, receives a higher amount of pheromone per time unit and therefore draws more ants to choose the shorter path, and continues to increase the density and strength of the pheromones. The idea of the ant colony algorithm is to mimic behavior with artificial ants, walking around the graph representing the problem to solve. The simulation results in emergent properties found in ant behavior. From stealing sugar cubes to finding solutions in a short path on a graph, who knew that ants and computation could go hand in hand? Thanks for watching.